Yo, what's up, guys? Welcome back to another video. And today we're gonna be talking about dot product, and this is like a very important topic to talk about because usually it gets introduced, I think, around near the end of your pre-cal slash calc one. It's like start of calc one classes, and it's very important because I made a vector video months ago and I kind of neglected that, so I'm sorry about that. I just been off, just been doing things and stuff, but I'm back now. So essentially, dot product is very important in the realms of calculus and physics. It's essentially like an introductory base into vectors, and then also it's very important when you get into physics stuff. Uh, and I'll talk about that like in a little bit right now. So essentially, the basis of what dot product is, essentially, is just how much two vectors overlap, or essentially go in the same direction. So you'll see that there's going to be another thing later on called cross product. That's a completely different thing. For dot product, you get a scalar value, which means it's just a number. So no matter what happens, if your dot product ends up in a vector, then you did something wrong, because you should always get a scalar number to it. And like I said, it can be used in a variety of ways. Most notably, this is a physics equation, so it's the integral from distance 1 to distance 2 of force times distance with respect to r, which is the position. Essentially, this is equal to work. I just butchered it right now. It's been a minute since I've thought about physics at all. But it's essentially, this is a famous line integral used to calculate work when something's moving a long distance. So I don't know. I thought it was pretty cool. I was learning about it because usually like people would teach you that it's just F times D, or force times distance, which is work. However, it goes like more in depth when you actually view the applicable ways it can be used in real life. But essentially, dot product is as simple as 1, 2, 3. So here we go. So essentially, let's say you had vector 1. Let's say u is equal to the vector 3, 2. And then v is equal to 5, 2. Essentially, what dot product is just u times v. U dot product v. This is a dot. I know it looks like a multiplication symbol. It's a dot. I promise you it's a dot. And essentially, we're going to label this A1, B1, and A2, B2. So essentially, the way you want to do this is, and this is my personal way, dot product is just a way of multiplying these two things together and then these two things together. So essentially, it's A1 times A2 plus B1 times B2, which is the way I represent it in my brain. It makes sense to me. So essentially it's 3 times 5 plus 2 times 2. 3 times 5 is 15 plus 4 is 19. And this is the dot product for these two vectors specifically. So it's really simple. Right now it's just, this is the 2D vector. It will always end up in a scalar. And so far, later in this video, I'll teach you what to do with this number specifically. But let's get into a 3D example. So let's say you have u again, which is equal to 3, 2, 1. Yeah, I know, very original of me. And then I'm going to switch the colors. V is equal to 5, 2, and 6. That's a 6. So essentially, you're going to do the same thing. Let's just say this is A1, B1. Then let's make this C1. This is A2, B2, C2. So again, you're going to multiply A1 times A2 plus B1 times B2 plus C1 times C2. This is going to be A1 times A2, which is 3 times 5, which is 15, plus B1 times B2, which is 4. And now we have the new C, which is 1 times 6, which is 6. Now you get 15 plus 4, which is 19, plus 6, which is equal to 25. and that's your dot product for a 3D vector. Essentially, it's the same. I don't know if you'd be going into 4D vectors, 5D, but it's essentially all the same. If you put out infinitely many numbers, the formula still stays the same. You multiply x by x, y by y, z by z if you get into that level, such as in Calculus 3. But so far, mostly for the level at Calculus 1, you only need to know about the 2D vectors. And this is the part where I start talking about orthogonal parallel vectors. So we have another equation coming up for dot product. So dot product is A times B, as I've shown you, but it could also be equal to the length of A times the length of B cosine theta. And like I showed you before, what you can do with this number, you're given two vectors. You can find the length of them using Pythagorean theorem, but you can also find the angle between them. And here's what I mean. Before I get into that, orthogonal and then parallel. I think everyone knows what parallel means. Two lines that never touch but go in the same direction. Essentially like this. They're never going to touch, which is a sad love story. But orthogonal is different. It means that you have two vectors that make exactly a 90-degree angle. That's what orthogonal means. So when you hear someone mention that these two vectors were orthogonal, that just means that they made a 90-degree angle with them. So essentially, since the dot product is just finding how much they overlap or how much they go in the same direction, that's essentially what it is. I don't know what else to say. But we have this cool new equation we can use in order to find the theta between them. So, oh, and also another thing, if the angle is greater than 90, then it's an obtuse angle. If it's less than 90, then it's an acute angle. So I don't know, I thought that was pretty cool. I don't know, man. I don't know. And then now we're gonna solve a bunch of test questions. So essentially, these are good questions, don't worry. So we have, let's say we had this vector, x4. We don't know what x is. Let's just say this is A, and then B is equal to 3, 6. So essentially, I don't know, let's just map out B for a second. This isn't dot product. I don't know. I thought this was pretty cool though. So 3 is like over here, and it's like well over here. So essentially, let's say that we have these two vectors. Now let's say that we had B and then we had A. Let's say we had the slope of B. What would make A parallel to B? Just take a moment to gather. I don't know, I thought this was pretty cool. This is a big tangent, but it is what it is. Essentially, in order to find it, you would just do the same as you would. In order to find this slope, you would just do y over x, or rise over run. Oh my god, I have no more battery on my thingy. So you would do y over x, which is a 6 over 3, which is equal to 2. So now, since this is the slope, you can just set the equation as well for A. So now in order to make A parallel, which is 2, you can just do 4 over x equal to 2. 4 equal to 2x when you multiply x. And then x is equal to 2. So A equal to 2, 4 would make your B parallel with this one. I don't know, I thought this was pretty cool. All right, now time to the fun stuff. Let's say we had two vectors. A is equal to 1, 2. Oh my god, I need to start writing these things, bro. I'm so washed. Then we have B is equal to 4, 5. And now, since we have this cool new equation, let's find the end. Let's find you know, something cool. And in case, you know, someone's ever thrown this equation at you for no reason, just know you can derive it from this. Because you have to do is divide the lengths of A and B, which is pretty cool as well. So essentially, in order to find cosine theta of the two vectors or the dot product, we're gonna have to do dot product on top over the lengths of A times B. So essentially, I like to find the lengths first, which makes it far easier for me. So the length of A is just Pythagoras theorem, which is 1 plus 2 squared, which is 4, which is equal to root 5. And now the length of B is equal to 4 plus 5, 4 squared plus 5 squared, which is equal to what, 16 plus 25, that's what, root 41? So now you just put these at the bottom right here. Now you find a dot product between them. So the dot product, again, is just x times x and then y times y. So you connect these together. So it's going to be 4, because 1 times 4 is 4, plus 10, which is equal to 14. So your cosine theta is equal to 14 over root 5 times root 41. And the amazing thing is you can even find the angle between these two vectors as well, because all you have to do in order to find that out is to just take the inverse operation of cosine, which is arc cosine. Isn't that pretty neat? So boom, you found your angle. Oh my god, I cannot speak. And let me show you why this works. So essentially, we have these two vectors, right? We have 1, 2, which is like around here, I guess. Yeah, around there. Then we're going to make this a different color. Then we have 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. Let's just say this is 5. Yeah, this is bad drawing skills, but hear me out, I swear. So essentially, what we're going to do is I'm going to pull up Desmos to see if this is an actual angle that can happen. Because I have no idea if this shit can even happen in real life. Oh, it can. Yeah, look. Yeah, 12 degrees of separation. You see, math works. Math fucking works. If you're able to get an angle between two vectors, it works. I promise you it works. And so we're gonna do the same operation, but now with the x being negative on A. And now even before doing that, let's just say we had negative 1, 2, which is around here. This is A. Then we have the same normal vector 4, 5. So essentially, we do the same thing. A dot B over length A, length B equal to cosine theta. So essentially, dot product here is going to be negative 1 times 4, which is negative 4, plus 2 times 5, which is 10, equal to 6. So you have 6 over the lengths, which is going to be the same, because Pythagorean theorem. And then you can just arc cosine this, equal to theta. And now, even though you just made a negative, you should get a vastly different answer, which would be 65 degrees. So this theta right here, you can see that is much larger in terms of separation. Therefore, they don't overlap as much to where they go, which is why this has a much larger angle than you can see here. Even from my bad drawing skills, you can see how as the vectors get closer, you have a smaller angle, whereas where you can clearly see the separation of the vectors, you can get the angle to be very, very different, which is why this is equal to like 65 degrees. I don't know, I just thought this was pretty cool. And then there's also a little neat trick as well. I believe that if your dot product is positive, or if it's greater than 0, then your angle will be acute. If your dot product is exactly 0, then you have a right angle, or both vectors are orthogonal. And if your dot product is negative, then that means you have an obtuse angle, or larger than 90 degrees. So let's see if my theory is right. Let's say we had, I don't know. Let's just say, like, for funsies, let's say we had like 1, 2. Man, I don't know. Let's have like, I don't know, -5 and 10. Why not? Why not? We'll see if this works. Oh, actually, never mind. Let me make this -10 and then 5. No, let's make this 3. Yeah, okay, we're gonna see if this works. I don't even know if this is gonna work myself, but you know what? It is what it is. So I'm gonna prove this to you. Let's see. So let's just say this is A, and then let's just say this is B. Dot product of A dot B, I need to stop saying A times B, is equal to -10, because 1 times -10 is -10, plus 6, which is equal to -4. So now you can find the length of A, which we established to be √5, where we have the same, and then the length of B is going to be 100 plus 9, which is equal to √109. But since our general dot product was -4, that means we should get an angle that's over 90 degrees. So let's see if that's true. So this is equal to cosine theta, and then our cosine is -4 over √5, then √109, equal to theta. Now I'm going to plug this into Desmos and see if I'm right. What if I get like an undefined? That'd be crazy. Oh my god. Yeah, no, wait. I get 99. Yeah, wait. Yeah, you're going to have to trust me on this one, I swear. I get about 100 degrees. It works. Math works. I'm telling you, math works. And funsies, we're going to do an angle. We're going to do 2 vectors that are clearly 90 degrees apart. We're going to do 0, 3, and then we're going to do 0, 5. I mean, we're going to do 5, 0. So in order to find the dot product, let's just say 1 is called A, then B is called 5, 0. We just do dot product. So 5 times 0 plus 3 times 0. This is all equal to 0. And before we knew it, we already knew these two were orthogonal. So, math works. Trust me on this one. Math works. And that's my last example for the video because I'm tired. And it's been a minute since I did a video, so I sound awkward right now. But, you know, if you stuck around to the end, thank you for watching. I swear I don't curse a lot in my videos. It's just that I got really excited because it's been a minute since I've actually done like anything productive. And honestly, this video was really hard to make. Even though the concept was simple, it was really hard for me to like pull out information. Essentially this, I forgot about physics, man. It traumatized me. I got traumatized by physics. I just have to take electricity and magnetism this semester. Oh, it's gonna be horrible. Oh no, but I'm up to it though. I'm up to the challenge, so you know, we'll see. I'm gonna have to do more line integrals and surface integrals and stuff. Hopefully y'all enjoyed the video. I'm tired. Man, you know, thank you for sticking around to the end. You know, thank you for watching, and goodbye.